Welcome to the next module of the Securium Bootcamp. In the previous module, we took a look at 101 security pitfalls and best practices related to writing smart contracts with Solidity on Ethereum. In this module, we'll take a look at 100 more such concepts. We will start by taking a look at those specifically related to tokens, and then we'll take a look at those related to the concept of guarded launches. And then we will up-level from looking at security issues at a Solidity or EVM level to those that are applicable at an application logic level. And those pitfalls come from software engineering aspects that have been developed and defined and refined over the last several decades. And those concepts should really be helpful to a great extent while analyzing security risks at an application logic level. And then finally, we will end by looking at 10 security design principles that were developed decades ago and have been widely used in all security aspects related to Web 2 and are equally applicable to Web 3 and Ethereum as well. We have discussed several aspects related to ERC20 tokens and their security pitfalls. This one is specifically related to the transfer and transfer from functions that allow transferring of ERC20 tokens between addresses. According to the specification, these should return Boolean values. However, not all token contracts adhere to the specification. So they may not return Boolean values, they may not return any value at all, or they may return a different value of a different type. In such cases where they do not return a Boolean value, callers that assume the Boolean values to be returned may fail. So the best practice here is for ERC20 token contracts to make sure that they are returning Boolean values, and for call sites to not make such assumptions about Boolean return values, and preferably use the safe ERC20 wrappers from OpenZeppelin that handle all the possible scenarios where Booleans are being returned or non-Booleans are being returned or no values are being returned and the contract simply revert. The ERC20 specification makes it optional for token contracts to implement name, symbol, and decimals primitives. As a result, any contract that is interacting with ERC20 contracts should make sure that these primitives are indeed present and implemented by those contracts if they want to use them. And the best practice is not to make an assumption that these primitives will always be implemented by the ERC20 contract because they are optional. ERC20 contracts have a notion of decimals, and they are typically 18 digits in precision. And therefore, the token standard specifies using an uint8 type to represent decimals, because that is sufficient to represent a value of 18. However, token contracts that do not adhere to the standard sometimes incorrectly use a uint256 type for decimals. And the best practice here is to check which type is being used by the ERC20 contract, and if it is a uint256 type, then have a further check to make sure that the decimal value is less than or equal to 255, because that is the maximum value that can fit within a uint8 as required by the token standard. We have talked about the race condition risk from the prove function of ERC20. To summarize it again, let's take a look at the same example that we discussed, where we have a token owner who has given an allowance of 100 tokens to a spender and then wants to later decrease that allowance to 50 tokens. The spender may be able to observe this decrease operation, and before that happens can front run it to first spend the 100 tokens for which they already had the allowance, tokens from earlier. And then once the Proof 50 operation succeeds, they further spend those 50 tokens as well. So effectively, they have ended up spending 150 tokens while the owner intended for them to only be able to spend 50 tokens. And this is possible because of front running, because of the race condition opportunity. And the best practice here is to not use the prove function, but instead use the increase or decrease allowance functions that do not have this risk. We have discussed the ERC 777 token standard, which aims to improve some of what are considered as shortcomings of the ERC 20 standard. And one of these improvements is the concept of the hooks. These hooks get called before send, transfer, mint, burn, and some of the other operations in these tokens. While they may enable a lot of interesting use cases, special care should be taken to make sure that these hooks do not make any external calls, because such calls can result in re-entrancy vulnerabilities. So the best practice with ERC 777 tokens is to check for their hooks and make sure that external calls are not being made. There's a concept of token deflation that may happen in ERC20 token contracts. Some of these token contracts may take a fee when tokens are being transferred from one address to another. And because of this fee, the number of tokens across all the user addresses will reduce over time when they are transferred between those addresses. So the number of tokens received by the target address may not be the same as the number of tokens sent by the sender. And this depends on the amount of fee and if the fee is being charged at all. So the best practices here with respect to token deflation are for token contracts to generally avoid the notion of a fee that causes deflation, because that could break assumptions with the contracts that interact with this token contract. And for smart contract applications that work with ERC20 contracts, they should be aware if those ERC20 contracts have this notion of deflation or not. And if so, make sure that their accounting logic takes care of this deflation. And this is more of a concern in smart contract applications that allow their users to interact with it using arbitrary ERC20 token contracts. And in such cases, consider a guarded launch approach where the initial set of ERC20 tokens that can be used with this contract do not have this notion of deflation. ERC20 contracts could also have the opposite effect of token inflation, where such contracts generate interest for their token holders, and this interest is distributed to these holders while they make transfers. This effectively increases the number of tokens that are held by the user addresses over time. And this effectively means that when such a token transfer happens, the recipient may receive more tokens than were sent that reflect the interest being distributed. So if the smart contract application is not aware of the ERC20 contract generating interest, then those interest tokens may end up getting trapped in the ERC20 contract without being realized. And the best practice is, again, are very similar to deflation. ERC20 contracts in general should avoid this notion of interest that causes inflation, because their interacting contracts may make an assumption that no such thing is happening, and that could break a lot of the critical assumptions leading to vulnerabilities. Or again, such smart contract applications could consider a guarded launch approach where the ERC20 tokens that they work with are known not to have this notion of interest and inflation. High token complexity is considered as a security risk. We have long known that complexity in general is very detrimental to security. The same aspect holds good for ERC20 token contracts. So these contracts should have a well-defined specification. They should really be implementing a very simple contract, because any unnecessary complexity could result in bugs. Developers could make errors while developing these complex features. It is also much harder to reason about these complex features, and definitely harder to find and fix bugs in such features. So the best practice is at a high level to avoid any unnecessary complexity when it comes to implementing token contracts. In computer science, there is a notion of separation of concerns, which says that in a computer application, there should be different sections, each of which addresses a very specific concern. This applies to smart contract applications as well that work with ERC20 token contracts. And in this case, what we mean is that ERC20 contracts should only or mostly have functions that are relevant to ERC20 tokens. They should not include any non-token related functions in that contract, because that could introduce additional complexity, and like we just discussed, complexity is detrimental to security because it could introduce bugs. So at a high level, one should avoid unnecessary complexity by bundling non-token related functions within a ERC20 token contract, because that increases likelihood of issues in general, or in the worst case, security vulnerabilities. ERC20 contracts should be working with a single token address. What this means is that there should be a single address that maintains the balances of different users interacting with that contract. And this effectively means that there is a single entry point for checking the balances of users. And this is because multiple addresses within a contract can result in multiple entry points for the different balances that are held or maintained by those addresses. And not being aware of these multiple addresses and their balances can result in accounting bugs. So the best practice is to make sure that an ERC20 contract works with a single address. We have talked about upgradability in the context of the proxy contact pattern in the previous modules. This upgradability is interesting in smart contract applications where the implementation part of the proxy can be changed to a newer version to introduce new features or to fix any bugs in the previous versions. But when it comes to ERC20 token contracts, upgradability is a concern. And the reason is because any change in functionality that is introduced by this upgradability is detrimental to the trust that the users place in these contracts. And the rationale is that these token functions in this contract are meant to be very simple. The mint, burn, and transfer functions are required to adhere to the specifications so that all the contracts or all the users interacting with this token contract are assured of the functionality implemented by these functions. So the best practice here is to make sure that these token contracts are not upgradable, and if an application is interacting with token contracts, to check and verify that it is not upgradable. Recall that in the context of token contracts, minting refers to the act of incrementing the account balances of addresses to which those new tokens are credited. And in this context of token minting, one should be aware of the contract owner having any extra capabilities over this functionality. And if this is the case, then a malicious owner could effectively mint an arbitrary number of tokens to any address of their choice, which, as you can imagine, is very detrimental to the security of the token contract, because all the other users using this contract and maintaining balances of these tokens in that contract will be affected because their relative share of tokens will be much smaller because of this malicious minting by the contract owner. So the best practice here is to be aware of any such extra capabilities over this minting functionality by the contract owner, because that could be abused. Recall from the previous module that the ability to pause certain contract functionality is part of what is known as a guarded launch. However, when this guarded launch approach is applied to ERC20 tokens and pausing some of their functionalities like minting, burning, or transferring, then that could be a concern, because the authorized owners who are allowed to pause and unpause such functionality, those owners or their addresses or accounts could be compromised, or they may even be malicious. In which case, such compromised accounts could pause the contract functionality and trapping the funds of all the users interacting with that contract. So the best practice here is to be aware of this risk, and when interacting with token contracts, to check and verify if those contracts are possible or not by certain authorized owners. While the concept of blacklisting is commonly used in security for a long time to prevent malicious actors or actions from abusing the system, this notion, when applied to ERC20 contracts, is of concern. The reason again is because authorized users who are allowed to create and maintain this blacklist by adding actors or actions into that list, or by taking them out of that list, those owners could be malicious or they could be compromised. And in such scenarios where a token contract has this notion of a blacklist, then because of such malicious or compromised owners, the users' funds could get trapped if their addresses are blacklisted. So the best practice is again to be aware of this risk and check and verify contracts to make sure that they do not have this notion of a blacklist, and if they do, be aware of what can go wrong. Let's now talk about the team behind the ERC20 project and the implications of that on any security aspects of that project. The team behind the ERC20 project may be publicly known, where we know who the project members are, what their past projects have been, and how they're connected within the community. Or this team could be anonymous, where the project members are only known by their handles on GitHub, Twitter, Telegram, or Discord, and we have very little information about what they have done in the past, or about their real world identities and how they are connected within the social circles of the community. In this context, there are two schools of thought. There is a school of thought that thinks that an anonymous team is riskier from a security perspective of that project, because we do not have good ways to evaluate what their reputation is within the social circles, within the community, based on their past projects, and so on. And in this case, the assumption is that there is a greater risk, a security risk to the project, because these anonymous teams could not be as concerned about security, because any security implications or exploits might not hurt their reputation from this project, or the team members could also be imagined to have left behind bugs or backdoors within the project, so that later they themselves could exploit the project and what is known as rugging the project. So this school of thought believes that such anonymous teams should meet a higher bar when it comes to security or security reviews. On the flip side, there is also a school of thought that believes that anonymity or pseudo-anonymity should not matter to the project, to the security of the project. Any of your past projects, based on who you are, what you have done, what your connections are within the community, should not really impact the security of a project. And that this project should be evaluated independently of who the project team members are. So, irrespective of which school of thought you may subscribe to, this is something to be kept in mind, because privacy and anonymity are really strong aspirational goals of Web3. And any such team risk could potentially translate into a legal risk for someone who may review such projects or interact with it as users. Let's now talk about token ownership and how that affects the security. Token ownership refers to who owns the tokens and how many tokens they own. And in scenarios where there are very few users who own a lot of those tokens, then such a ownership situation will allow those owners to influence the price of those tokens, to influence the liquidity of those tokens, and also influence any potential governance actions around those tokens, because those actions will be controlled by the token ownership. So this is an aspect of risk from centralization, because there are very few owners holding a lot of tokens, and this risk could manifest itself into a security risk as well. A related concept is that of token supply. Token supply refers to the number of ERC20 tokens that is supported by this token contract. And this supply depends on what has been implemented for that particular contract and application, but it could be low or it could be high. And the concerning situation is when a particular ERC20 contract has a very low supply of its tokens. Because this, by implication, means that the ownership may end up being concentrated within a few owners who own a significant part of the supply. In which case, they have a significant influence over the price of those tokens, their liquidity, and therefore their volatility. So this scenario brings in an increased manipulation risk for such tokens with limited supply, and is something to be aware of. ERC20 tokens get listed in various places to allow trading between users. These tokens may get listed on centralized exchanges or decentralized exchanges. Decentralized exchanges are expected to be more resilient to failures, and therefore are expected to be up and accessible all the time. However, if a token is listed on very few centralized exchanges, and those exchanges happen to be inaccessible because they're down for maintenance, or maybe in extreme situations where they're hacked, then that is a concern, because the majority of the tokens will now be inaccessible. And because of this low liquidity, the price volatility of such tokens will be very high. So this is another aspect of centralization risk that one should be aware of when looking at tokens that are listed in very few exchanges. Assumptions on token balances pose a security risk. Smart contract applications, where the logic assumes that the balance of tokens that it is working with is always below a certain threshold, stand the risk of those assumptions breaking if the balance exceeds those thresholds. And this may be triggered by users who own such a large number of tokens and who are typically known as whales, or they may also be triggered by what are known as flash loans. A flash loan is a capability where a user is allowed to borrow a significant number of tokens without providing any collateral, but this loan has to be repaid or is forced to be repaid within the transaction itself. So by the end of the transaction, the flash loan capability makes sure that the tokens that were lent to the user is paid back to that contract. But within that context of the transaction, the user has access to a significant number of tokens as provided by that flash loan contract. And such a use of large funds or flash loans may be used by users or attackers to amplify arbitrage opportunities or exploit vulnerabilities where the logic incorrectly depends on low token balances. So this risk from large funds or flash loans needs to be kept in mind because it could be manipulated.